The first number that we looked at was 400 billion. That's the upper bound for the number of stars estimated to be in our galaxy. That's a 4 followed by 11 zeros, as we can see in the scientific notation. Second set of numbers that I want to concentrate on were those where we had a machine that would replicate itself, with each iteration being twice as big as the previous. So we started with 1, then 2, then 4, 8, 16, 32, 64, 128, 256, 512, 1024. Those numbers can be expressed as powers of 2. Remember, this is an exponential growth curve where the base was 2. So these are all powers of 2. And the exponent is x, but we could think of x as being the level that we're on. Now that figure on the right-hand side, that 1024, represents 2 to the 10th power, 2 multiplied by itself 10 times. If I was to complete another line of these figures, then the number underneath 1024 would be the corresponding power of 10, 2 to the power of 20, 1,048,576, because it's just 1024 squared. Now this is where it gets interesting. If I look down to the corresponding power of 2 underneath that, that would be 2 to the power of 30. That's 2 to the 20 times another 2 to the 10, which is approximately 1,000,000 times 1,000. And it works out to be exactly 1,073,741,876. So already we're over 1 billion just at the 30th power. Now looking down at the equivalent position on the fourth line, we get to a number which is over 1 trillion. Turns out to be 1,099,511,627,776. So already we're beyond the total number of iterations that we need, or the total number of stars that we estimated originally. Recall that we were assuming an upper bound of 400 billion. Well, that's just under half a trillion, and we're already over 1 trillion at this point with that power of 2. So if we go back a couple of powers of 2, so if we look at 2 to the power of 38, that's this figure of 2 to the 40 divided by 4, turns out. That gives us 274,877,906,944. Now that's about just over 250 million. And that is actually sufficient for us to stop at, because we're not looking for the term which gives us greater than or equal to 400 billion. We're actually summing up these terms. And so if we sum all the terms to and including that term, we've already reached over 400 billion. Here's a brief explanation. Suppose we were to sum the first 5 terms, which are 1, 2, 4, 8, and 16. The answer we get is 31, which is 1 less than 32, which is 2 to the power of 5. If we were to sum the first 6 terms, that's 1, 2, 4, 8, 16, and 32, we would get 63. That's 1 less than 64, which is 2 to the power of 6. So if we were to sum the first 38 terms, what we would end up with is 1 less than 2 to the power of 39. So reiterating, when we sum all of the terms up to and including 2 to the power of 38, that's equivalent to 2 times 2 to the 38 minus 1. So we'll get a number which is greater than 500 billion. And that is more than the upper bound that we assumed for the number of stars in the galaxy, being 400 billion. So that index, or that power of 38, is the number of iterations we need in order to populate every star system in the galaxy. That's 38 iterations. Now let's do a little maths. Each iteration represents a journey between 2 stars, and at the start of this we assumed that the distance between any 2 stars would be the maximum possible distance, that being 100,000 light years. The diameter of the galaxy, and it would be that for every pair of stars. Now, if it was possible to travel at the speed of light, that would mean that that journey would take 100,000 years. And there are 37 of these iterations in order to populate the galaxy, 37 successive iterations. So that means 37 times 100,000, which gives us 3.7 million years. and that's to colonize or to reach every star system within our galaxy. Now suppose that we assume more realistically that we can't travel at the speed of light, but perhaps a significant fraction, like 10% the speed of light. That means those journeys would take not 100,000 years, but 1 million years. Even so, 37 successive journeys would add up to 37 million years. Even if we assume that we could only travel at 1% of the speed of light, that means each journey would now take 10 million years. But 37 of those journeys successively, 370 million years. And that is a vanishingly small fraction of the age of our galaxy and of our universe. So a question that we might ask is, if someone or something was to do this, then we should expect to see the galaxy populated with life. So in our observations, we haven't yet seen that. Why is that? I don't want to draw any conclusions, but I'm just pointing out, quite interestingly, the mathematics that we could use to go about such an experiment.